Hey there. So in this video, we'll continue our journey of understanding the 1970s model of computation. And let's just recall that we mentioned that there was like a CPU and a memory. The CPU would float an address and the memory would kind of return back data, right? Data on the data bus. And, we then added another line here, which was the read write line, and mentioned that, anytime the CPU could essentially convey whether it wanted to read data or write data. And then we also mentioned, depending on what phase the CPU is in, the data being sent over the wires, that might be an instruction or the actual data to be processed, right? And then in the previous video, what we did was we discussed heavily about the memory, right? And then what we came up with was the model for memory as a bunch of registers, each one of them having an address, so on and so forth. We mentioned each of the register was 1 byte in size, and then the fact that there was like some circuit here, but externally it would take in an address, which is essentially a number, and then it would either take in another number as data to be written or data to be returned back to the CPU, depending on another line called the read write bar. Yeah, and then we somewhere also mentioned that it has like a clock, like on the ticks of which the memory operates. Okay, so now what we're going to do is we are going to focus on the CPU and build a mental model for the CPU, how you should think about the CPU so that you can reason through your program correctly, right? So let me first go ahead and maybe, just draw a block diagram for the CPU. So this is a CPU, and externally what we should be able to make out of this diagram is it has an address bus, right? And then it has a data bus, right? Oh, okay, data bus, right? And so these connections are going towards the memory, and then obviously we also have, so we also have the read and write bar to convey whether it wants to read or write. Now, what I'm going to tell you is formally also referred to as the programmer's model of the CPU. Yeah. So if you were to search online for any of the CPUs of your choice, the programmer's model, you will find something, right? And that will be along these lines. Now the thing is, what I'm going to explain only forms part of the programmer's model, because the programmer's model has many things within it, many subtopics, but we are taking a look at the part that helps us the most when considering understanding the C language, right? Okay, so we then know that it has like the address bus, data bus, read write bar, those lines. So my claim now is that internal to the CPU, there is something called register file, right? And the register here is the same register that we saw in the previous video. It's the same register that forms the byte in the memory, right? Now, so this has register file, and then that register file has many registers, right? And depending on the number of bits that the CPU can process, these registers will have a width. So on a 32-bit machine, this would be a 32-bit register file. So each register is kind of 32-bit, right? And so let's just name them x0, x1, x2, x3, just for simplicity, right? And so on. And let's say there are 32 of those. So typically the registers would be very limited in number within the CPU. And typically 32 or 64 is like the typical number I have heard of. And these are also called GPRs, or general um, general purpose registers. Right? And the idea is that these will be used for computation by the CPU. And we'll talk about that in a while. But know that the general purpose registers are what the CPU will use to do the calculations. Right? Okay. Then the CPU also has a bunch of other registers, another register file if you would want. You could think of it that way. And these are called the special function registers. Right? So SFRs. An alternate name for these are called configuration registers. Right, and then these are referred to as CFRs. Right, configuration registers or special purpose registers. Now, what are these? Right, so if the CPU does any calculation, let's say it adds two numbers or subtracts two numbers, then it needs to somehow track the status of what the calculation was. Was it a zero? Was it a negative number? Was it like an overflow that 32 bits could not contain the answer? So there is a dedicated register for that. Within that there would be bits, and each of the bits convey some information like that. A negative number was generated, there was like an overflow or something like that, and that is typically called the program status register. Right. So that one register which has the status of the program, what values it generated, that will be in the PSR or the program status register. Now each CPU has a different name for this register, but typically the CPUs would have this. Right. Then there are other registers which are tracking special things. So for example, there would be something called program counter. We'll come to it. Then there would be some other register which is controlling the features of the CPU. Things like should the CPU do floating point operation, or should the floating point be off? So things of those nature. So the special function registers and the general purpose registers, my claim is that completes the programmer's, not completes, but that is enough as a programmer's model for us to be able to write and understand the C program and even assembly programs. Now, if you have studied computer organization or any introduction to computer architecture, you would know that the CPU internally has many circuits like the ALU, then there is like a control unit, then there is some more circuits. We don't look at the circuits at all, no circuits. We don't care about it, right? We only work with this from programmer's standpoint. The CPU is just bunch of registers. Right? We do not have to bother, and we actually do not care at this point about the internal implementation of that CPU. You don't have to know what gates are used, what digital circuit is used, what are the voltage levels, none of that. What does the control unit look like, how it's implemented, how it works? You don't have to know any of that, right? So again, to reiterate, we only care about CPU as a from programmer's perspective, as a bunch of registers, right? And then the other thing that I did not draw here, but usually exists on CPU, is the ability to receive external signals called interrupts. So interrupts are essentially external lines to the CPU. It'll either be one or two of them, and that's essentially, you can think of it as a way that the CPU is executing a program, and then all of a sudden you want it to attend to, let's say, a timer event, for example, right? So that timer event, the fact that CPU needs to do something else, that would be conveyed using the interrupts. So we'll discuss about interrupts also bit later in the series, but from our current standpoint, A CPU is just a bunch of registers, right? Okay, now then the question is, another thing we need to know about the CPU at this point, before we dig deeper into how the CPU processes data, is we talked about memory and CPU, then CPU having registers, right? There is only one register that we need to remember right now, which is called the PC, which is called the program counter. Now we talked about the fact that some part of the memory might contain code and some might contain data, right? And well, essentially the memory just has bits, and I was mentioning that based on what address it floats and what data gets returned, for example, and depending on which phase the CPU is in, it might treat that data as an instruction, right? So the program counter is that register which will be pointing to the instruction to execute next. So if program counter has the address, let's say hex 8, hex 8 is the memory location whose content will be fetched and treated like an instruction by the CPU, right? So that is one thing. And we'll talk more about how the internals of CPU are, again, elaborating a little more on the programmer's model. But right now, all we have to again remember is a CPU is a bunch of registers. And then before we close off for today, the final thing that I want you to dwell on is we'll be looking at something called the load store architecture. So formally, we'll be looking at the load store architecture. What that means is that within the CPU, the GPRs that we have, we'll float an address and get the data from the memory into one of the GPRs, right? And then we'll float another address and get another data into another, GPR. And then we'll process these. You don't have to process like 2 of the data. You can also fetch just 1 of the data byte and process just that. Then all of that is allowed. The idea is that you first fetch the data into the CPU registers, the general purpose registers, operate on them, update registers locally inside the CPU, and then float the address again and issue a write transaction, right? And take this value and write it somewhere in the memory. So what we did was we first copied the data from memory to CPU. That was the load operation. We processed it, the CPU processed it, and once all of that was done, it was saved back to the memory, and that's called the store operation. So moving forward, what we are going to do is imagine the CPU to be a bunch of registers with external interrupt lines that we'll discuss a bit later in the series. And then the CPU also has certain buses to interact with the memory. And then finally, the CPU always gets the data first into the general purpose registers, referred to as load, and then processes and stores it back into memory, called the store operation. And I suppose with this, we can close the video for today, and I'll see you in the next one.